Only weeks ago, astronomers anticipated that 3I/Atlas, humanity's third confirmed interstellar visitor, would drift quietly past Mars without fanfare. What transpired instead defied all expectations. Within a mere 48 hours, this enigmatic object erupted into brilliant activity, blazing 6 times brighter than any cometary model had predicted. It constructed a massive green cloud charged with carbon dioxide, stretching half the width of the Sun itself. Now Earth's most powerful telescopes stand helpless as Atlas hurtles toward Mars at nearly 70 kilometers per second, vanishing into blinding solar glare. Why is this alleged alien traveler shattering every known rule? Does it herald new physics, or conceal something far more mysterious? What secrets are unfolding near the red planet? And can anyone on Earth decipher them before time runs out? At this moment, 3I/Atlas sits approximately 2 astronomical units from the Sun, twice Earth's distance from our parent star, or nearly 300 million kilometers away. It tears through space at a staggering 58 kilometers per second, a velocity that challenges human comprehension. This speed exceeds that of any planet in our solar system by a comfortable margin. Mercury, our fastest planet, orbits at just under 48 kilometers per second. At its current pace, 3I/Atlas could traverse the gap between Earth and the Moon in slightly over an hour, a journey that required 3 full days for Apollo astronauts. As it approaches perihelion at October's end, its velocity will surge even higher, reaching nearly 68 kilometers per second, an extreme that pushes the limits for natural objects within the inner solar system. For perspective, consider the Parker Solar Probe, humanity's fastest creation, which will eventually achieve speeds around 200 kilometers per second, but only after years of gravity assist and meticulous planning. 3I/Atlas achieves its breakneck velocity simply by falling, drawn inexorably by the Sun's gravity along a hyperbolic trajectory. On the astronomical magnitude scale, 3I/Atlas has brightened to magnitude 12. While this number might seem abstract, it carries profound implications. The faintest stars visible to the naked eye hover around magnitude 6. Each step on this scale represents a dramatic change in luminosity. A difference of 5 magnitudes translates to a 100-fold shift in brightness. The jump from magnitude 16 to 12, as witnessed with 3I/Atlas, represents an increase of roughly 40 times in brightness. Yet even at this intensity, the comet remains completely invisible to unaided human eyes. Only observers wielding mid-sized telescopes under clear, dark skies can catch a fleeting glimpse. For most amateur astronomers, it appears as nothing more than a ghostly smudge, barely distinguishable from the background noise of space. The comet's brightness transcends mere optical considerations. It reflects the sheer volume of sunlight being scattered by its rapidly expanding coma. The nucleus of 3I/Atlas remains hidden, shrouded beneath a dense cloud of gas and dust. Size estimates for this concealed core range from a compact 0.3 kilometers to a more substantial 5.6 kilometers across. The coma, the luminous envelope enveloping the nucleus, has swollen to nearly half the Sun's diameter. This is no mere visual illusion. The coma constitutes a genuine physical structure, hundreds of thousands of kilometers wide, composed of ice and dust vaporized by the Sun's relentless heat. It reflects and scatters sunlight on a scale rarely witnessed at this distance from our star, marking 3I/Atlas as a profound outlier among comets. Trajectory calculations confirm beyond doubt that 3I/Atlas follows a hyperbolic path. It is not gravitationally bound to the Sun. This represents a one-time passage through our solar system, never to return. Its closest approach to Earth will reach no nearer than 1.8 astronomical units, eliminating any danger of impact or debris strikes. The true urgency lies elsewhere, in the fleeting opportunity to observe an interstellar visitor as it races through our cosmic neighborhood, soon to vanish forever into the Sun's overwhelming glare. Every metric, distance, velocity, brightness, places 3I/Atlas far beyond the familiar patterns of solar system objects. The numbers resist easy comparison, defying the comfortable frameworks astronomers typically employ. With a Mars flyby imminent, these facts establish the baseline, anchoring our story in hard, unyielding data. Within hours of the brightness spike, the Comet Observation Database (COBS) exploded with alerts. Amateur astronomers in Australia posted the first flag measurements, documenting a six-fold increase in light output over just 2 nights. Was this a genuine outburst, or merely an artifact of photometric scatter and observer error? The question demanded immediate investigation. On October 3rd, 3I/Atlas sweeps past Mars at a distance of approximately 30 million kilometers, closed by cosmic standards, yet still safely outside any risk zone for the red planet or its orbiting spacecraft. The comet's trajectory is relentlessly outbound, defined by an eccentricity greater than 1. That number, simple though it sounds, carries immense meaning. The object is unbound, an interstellar visitor executing a single, irreversible pass through our solar system before vanishing into the depths of interstellar space. For Earth, the closest approach has already occurred, never dipping below 1.8 astronomical units. In practical terms, that's more than 270 million kilometers, nearly twice our distance to the Sun. No debris threat, no impact risk, no meteor storm. The only thing at stake is the data we can collect while the observation window remains open. But that window is contracting with alarming speed. As 3I/Atlas barrels inward, the geometry of its path conspires against ground-based astronomers. The angle between the comet and the Sun, known as solar elongation, narrows with each passing day. By October 21st, this angle will dip below 30 degrees, a critical threshold. Below that point, even the most advanced telescopes struggle to distinguish the comet's faint glow from the overwhelming brightness of the twilight sky. For most observers, the practical viewing window slams shut in early October, precisely as the comet makes its closest approach to Mars. The timing is brutally unforgiving. Perihelion arrives on October 29th or 30th, when 3I/Atlas will pass within 1.36 to 1.4 astronomical units of the Sun. At that pivotal moment, its velocity peaks near 68 kilometers per second, and its activity is expected to reach maximum intensity. Yet from Earth's perspective, the comet will be utterly lost in solar glare, invisible even to our largest observatories. This blackout period, spanning from early October through early November, means that the most dramatic phase of the comet's evolution will unfold entirely beyond the reach of direct human observation. All of this has been mapped with precision by orbital modeling, which tracks every nuance of the comet's path using data compiled from hundreds of observations. The numbers are unambiguous and absolute. 3I/Atlas will not return. Its hyperbolic trajectory guarantees that any mysteries left unsolved in the coming weeks will remain unanswered for generations. The urgency is genuine, though it stems not from danger but from the extraordinary chance to witness an object from another star system as it interacts with our sun and planets before slipping away forever into the cosmic void. The only way to extend our observation window now is to hand off the surveillance to spacecraft already circling Mars, each armed with its own suite of sophisticated instruments, each with its own opportunity to capture fragments of this fleeting encounter. The scramble for data ignited the moment 3I/Atlas deviated from its predicted behavior. Observatory schedulers across the globe found themselves locked in a desperate race, against time, against the sun, against the limitations of their instruments. With the comet's light curve veering sharply upward, major facilities activated, target of opportunity, protocols reserved for the most urgent cosmic events. The Hubble Space Telescope, already oversubscribed with competing priorities, carved out an emergency imaging slot, capturing ultraviolet and optical frames as the coma ballooned to unprecedented proportions. Each Hubble exposure demanded a delicate balance. Avoid saturation from the comet's increasing brightness while preserving the fine detail necessary for scientific analysis. Instrument teams recalibrated settings on the fly, adjusting parameters in near real time to keep pace with the comet's rapid evolution. Close behind, the James Webb Space Telescope secured a rare committee-approved observation window for mid-infrared spectroscopy. On August 6, JWST's NIR-SPEC instrument locked onto the expanding coma, registering an unusually elevated carbon dioxide to water ratio of approximately 7.6, far exceeding the norm for solar system comets. This finding, immediately flagged to the Minor Planet Center and shared through private astronomical Slack channels, triggered a cascade of requests for additional spectral coverage from observatories worldwide. The Gemini South Observatory, operating from its perch in Chile, pivoted next, capturing a sequence of optical and near-infrared snapshots. Gemini's wide field of view and rapid filter switching capabilities allowed teams to monitor subtle changes in coma structure and color evolution, even as the object's brightness fluctuated dramatically from night to night. Meanwhile, SphereX, NASA's all-sky infrared surveyor, adjusted its normal scan cadence to catch brief glimpses of the comet's evolving spectrum. Though SphereX wasn't designed for rapid target follow-up, its broad wavelength coverage provided a unique baseline for tracking volatile emissions as the comet traversed different solar distances and heating regimes. Each facility brought distinct strengths and equally distinct constraints. Hubble could resolve fine structural features in the coma, but only during narrow, precious time slots. JWST delivered unmatched sensitivity in the infrared spectrum, but scheduling remained tight with numerous other high-priority targets queued for the same observation windows. Gemini's ground-based vantage point was perpetually limited by weather conditions and the comet's shrinking solar elongation. Coordinating these diverse assets required a level of choreography more commonly associated with planetary defense exercises than routine comet observations. Observatory directors juggled competing requests from multiple science teams while data pipelines ran through night to process and distribute raw frames. Slack threads filled with intense debates over optimal filter choices and exposure times. Every single observation had to count. The sense of urgency was sharpened by the approaching blackout. Once the comet slipped into the sun's blinding glare, Earth-based telescopes would be rendered completely blind for weeks. The final usable datasets, Hubble's ultraviolet images, JWST's carbon dioxide spectra, Gemini's color snapshots, would serve as the last record from Earth's perspective before the handoff to Mars orbiters. With that transition looming, the ground-based campaign became a crucial test of global scientific coordination, extracting every possible measurement from a rapidly vanishing target. When Earth's telescopes are blinded by solar glare, Mars transforms into the solar system's premier observation post. Orbiters circling the red planet suddenly find themselves tasked with tracking a comet that featured in no one's original mission plans. Each spacecraft brings a specialized instrument suite, and teams of engineers and scientists scramble to adapt, reprogramming systems and negotiating for precious observation time. HiRISE, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter, is renowned for its ability to resolve objects as small as a desk from Martian orbit. With a resolution of 0.3 meters per pixel, HiRISE could theoretically spot the nucleus of 3I/Atlas, assuming the background glare and tracking geometry cooperate. But tracking a comet moving at 58 kilometers per second, millions of kilometers distant, pushes both hardware and software to their absolute limits. Teams at the University of Arizona and JPL run intensive simulations, adjust exposure times, and compete fiercely for imaging windows. The risk isn't merely missing the comet. It's potentially overexposing the camera or damaging pixels if the sun inadvertently creeps into the field of view. ESA's Mars Express, orbiting since 2003, deploys the high-resolution stereo camera HRSC. HRSC excels at wide-field multi-angle imaging, ideal for capturing the full sweep of a comet's coma and tail. Its color filters help distinguish dust from gas components, while stereo image pairs may reveal subtle three-dimensional structures within the expanding cloud. The HRSC operations team in Germany coordinates closely with ground-based astronomers, timing exposures for optimal moments when 3I/Atlas passes nearest to Mars's orbital plane. The ExoMars Trace Gas Orbiter, TGO, carries CASIS, the color and stereo surface imaging system, and NOMAD, a sophisticated suite of spectrometers designed to detect faint atmospheric gases. CASIS, originally designed for Martian geology, can be retasked to image the comet's coma across multiple color bands. Its rapid imaging capability enables tracking of brightness and structural changes during a single flyby sequence. NOMAD is optimized for detecting trace gases like CO2, H2O, and rare organic compounds. By directing its spectrometers toward 3I/Atlas, the team hopes to confirm the elevated CO2 levels first flagged by JWST and search for chemical signatures never before observed in solar system comets. NASA's MAVEN mission joins the effort with a different perspective. Its imaging ultraviolet spectrograph tunes into emissions from atomic oxygen and carbon, while plasma instruments measure how the solar wind interacts with the comet's outflowing material. MAVEN's data could reveal whether the comet's distinctive green glow is driven by atomic oxygen or more exotic processes. Its orbit, designed to sample Mars's upper atmosphere, positions it perfectly to catch the comet's passage from multiple angles throughout the flyby. Mission operations centers across the United States and Europe convene emergency meetings, carefully weighing the risks of diverting instruments from routine Mars science operations. Every observation slot becomes a complex negotiation among engineers, principal investigators, and project managers. Safety protocols are stringent and non-negotiable. Cameras must avoid direct sunlight exposure. Spectrometers require meticulous calibration. Dust hazard models must be verified. Sometimes software patches are uploaded at the 11th hour to enable new tracking modes or override default safety limits that would otherwise prevent these unconventional observations. No single orbiter can capture the complete story of 3I/Atlas. Together, however, this international fleet forms a synthetic observatory, stitching together imaging, spectroscopy, and plasma measurements across different orbits and time zones. The ingenuity lies not merely in the hardware, but in the rapid coordination of teams who, until recently, had never even heard of this comet. As Earth's view fades into solar blindness, the responsibility for decoding this interstellar visitor passes entirely to these robotic eyes circling Mars, each one poised to gather data that could fundamentally reshape our understanding of comets and the chemistry of objects originating beyond our solar system. Color in a comet's coma serves as a chemical fingerprint, shaped by sunlight and the volatile ices boiling away from its frozen core. In September, 3I/Atlas stunned the astronomical community as its coma underwent a dramatic transformation from muted red to vivid, brilliant green, a shift that signaled something highly unusual was occurring deep within its expanding envelope. The coma's sheer size proved difficult to comprehend. Spanning nearly half the diameter of the Sun itself, stretching over 600,000 kilometers across. This wasn't a photographic illusion or a trick of overexposure. The green luminescence was real, physical, and demanded a rigorous explanation. Traditionally, green comets owe their distinctive color to diatomic carbon C2, which fluoresces in the swan bands near 510 nanometers when struck by solar radiation. Yet as spectroscopists pored over data from Gemini, the Very Large Telescope in JWST, the expected C2 emission lines were conspicuously absent. No swan bands, no trace of the classic carbon signature, even as the coma's brightness intensified dramatically. Instead, the spectra pointed toward a different culprit entirely. JWST's August observations revealed a CO2 to H2O ratio of approximately 7.6, an extraordinary value far exceeding that found in most solar system comets, where water ice typically dominates the composition. This finding redirected attention to atomic oxygen, specifically the forbidden OI emission at 557.7 nanometers, 5,577 angstroms. This characteristic green line appears when sunlight and energetic electrons break apart CO2 and H2O molecules, liberating oxygen atoms that emit green photons as they relax from a metastable excited state. In the dense CO2-rich coma of 3I/Atlas, solar ultraviolet radiation and photoelectrons act as powerful catalysts, transforming the region into a factory for green Y emission. Laboratory experiments and previous comet studies support this mechanism, but 3I/Atlas pushes it to unprecedented extremes. Even at 2 astronomical units from the Sun, conditions prove ideal for this process to dominate, outshining the dust scatter continuum and producing the eerie green glow that now defines the comet's appearance. Alternative explanations have been rigorously considered and largely ruled out. Research teams search for CO fluorescence, unusual dust scattering properties, and rare plasma effects. But the conspicuous absence of CO in the unchanged dust spectrum rendered these alternatives unlikely. The scientific debate unfolded in real time, with researchers sharing raw spectra and calibration scripts across continents, meticulously dissecting every new data released for traces of C2 or other carbon chains. Yet the consensus solidified around atomic oxygen as the primary driver of the green coloration. The timing proved compelling. The green phase commenced precisely as CO2 output surged, and as the comet crossed a threshold where solar UV radiation could efficiently photodissociate molecules within expanding coma. Dr. Lena Sato, lead spectroscopist with the JWST observation team, described the challenge as chasing a moving target with a shifting personality. Each spectrum captures a system in constant flux, where chemistry and physics collide on a scale rarely witnessed. The absence of C2 wasn't a scientific failure. It was a crucial clue suggesting that 3I/Atlas operates under chemical rules unfamiliar to typical solar system comets. The green glow became its defining signature, a marker of interstellar chemistry, and ancient ices shaped in the nursery of another star. The puzzle remains tantalizingly open. As the coma continues to evolve and Mars orbiters prepare for their observation campaigns, the search for definitive spectral lines, C2I, or something stranger still, continues with intensity. Each new measurement could reveal whether 3I/Atlas is simply a comet pushed to its physical limits, or a messenger carrying secrets from beyond our solar neighborhood. The next question looms: how does this exotic chemistry shape the comet's overall structure? And what might the mysterious anti-tail reveal about the forces sculpting this alien visitor? A sunward streak slices through the coma of 3I/Atlas, running counter to the classic image of a comet's tail. Instead of streaming away from the sun, this anti-tail points directly toward it, visible in both Hubble images and ground-based telescope observations. The conventional explanation, a projection effect when Earth crosses a comet's orbital plane, doesn't fit the observed geometry. The angles are wrong, and the anti-tail's persistence over multiple weeks hints at a more fundamental cause. Plasma physicists and dynamicists have focused intently on the underlying mechanics. 3I/Atlas is dominated by carbon dioxide rather than water ice, and its outgassing activity is far from uniform. Sunlight strikes the nucleus at a steep angle, driving powerful jets of gas and dust primarily from the sunward hemisphere. This asymmetric activity propels large dust grains outward, but not evenly in all directions. The most vigorous jets occur where solar heating is most intense, stretching a snow line farther toward the sun than observed in typical comets. Grains launched along this sunward axis are both larger and slower moving, enabling them to survive both radiation pressure and intense heat for much longer periods. The result: a genuine physical anti-tail, an arc of massive grains that can persist for tens of thousands of kilometers before finally sublimating into gas. Models indicate these grains measure at least 10 microns across, massive enough to resist solar wind pressure and maintain their sunward trajectory. Their survival depends critically on both size and composition. While pure carbon dioxide ice vaporizes rapidly under solar heating, grains mixed with darker, less volatile materials can endure long enough to create the observed feature. The anti-tail's brightness decreases exponentially along its axis, precisely matching theoretical predictions for when grains are steadily destroyed by solar radiation, not merely scattered through space. Electromagnetic forces add another layer of complexity. As the coma expands, it becomes a natural laboratory for studying plasma interactions. Electrically charged dust grains interact with both the solar wind and the comet's own material outflow, creating narrow streams and spikes that can distort the anti-tail's appearance. Still, for 3I/Atlas, the primary sunward feature appears driven by grain survival physics and anisotropic jet activity, not exotic plasma effects. The ion tail, shaped by the interplanetary magnetic field, points away from the sun as expected, clearly separated from the anti-tail's trajectory. Some observers have speculated about non-natural causes, engineered structures, self-organizing plasma phenomena, even interstellar technology. But the accumulated data don't support these extraordinary claims. Every observed feature fits comfortably within the boundaries of known cometary physics, albeit pushed to extremes by the comet's unique chemistry and activity levels. Dr. Rafael Ortiz, a plasma physicist involved in the Mars Orbiter Observation Campaign, summarizes the situation succinctly. If you want proof of the extraordinary, you must first systematically rule out the ordinary. So far, the anti-tail represents a triumph of natural mechanics operating under extreme conditions. The definitive test still lies ahead. As 3I/Atlas rounds the Sun and Mars orbiters gather their data, models of grain-size distributions, jet anisotropy, and plasma coupling will face their most rigorous challenge yet. If the anti-tail fades or fragments, as predicted for carbon dioxide-driven grain populations, the case for a natural origin grows substantially stronger. If it doesn't behave as expected, new physics may indeed be waiting to be discovered. After perihelion, 3I/Atlas enters its most unpredictable phase. Scientific models diverge into competing camps, each presenting a different vision for what happens next. Some researchers forecast a gradual fade, brightness declining steadily as volatile ices are exhausted and the Comet contracts, leaving only a faint remnant to drift outward into interstellar space. Others warn of a final dramatic flare, a surge in brightness triggered by fresh reservoirs of carbon dioxide suddenly exposed, or a catastrophic collapse of the nucleus itself, echoing the fate of comets that have fragmented spectacularly under extreme solar stress. A third possibility lingers on every dynamicist scorecard: complete disintegration. If the nucleus is as porous and structurally compromised as its violent activity suggests, perihelion could trigger its breakup, scattering fragments that would briefly spike the light curve before vanishing forever into the void. Dr. Mara Valente, a comet dynamicist tracking the event closely, describes the upcoming weeks as a stress test for every theory we hold about interstellar wanderers. Her research group simulations map out dozens of potential scenarios, each tied to specific observable diagnostics. A smooth, monotonic decline in brightness would suggest simple outgassing depletion. Erratic jumps or sudden drops could signal fragmentation events. A persistent green coma after perihelion would point to deep reservoirs of carbon dioxide-rich ice, while a rapid color shift back to red or blue might reveal the exhaustion of those volatile surface layers. The stakes extend far beyond understanding the fate of a single comet. 3I/Atlas serves as an active probe from another star system, carrying chemistry and structure forged in a distant stellar nursery millions of years ago. Its behavior tests the fundamental limits of comet physics: how deeply buried ices survive the rigors of interstellar travel, how dust and gas interact with solar wind under extreme conditions, and whether our current models can accurately predict the life cycles of objects that spend eons drifting between stars. Each potential outcome, fade, flare, or fragment, feeds critical data back into planetary defense models, refining how we track and interpret new arrivals that might one day pose a genuine threat to Earth. Speculative ideas, from engineered interstellar probes to exotic living plasma, remain firmly on the scientific fringe. No accumulated evidence supports such extraordinary claims, but the scientific method demands unwavering vigilance. Every anomaly must be rigorously checked against natural explanations before invoking phenomena beyond our current understanding. The Mars flyby and perihelion observation window create a rare natural laboratory, one where model predictions can be directly scored against real-time events, and where the boundaries between the known and the possible are tested under the most demanding conditions. Key milestones are already circled on calendars worldwide. Mars orbiter data releases in early October, perihelion on October 29 to 30th, and the return of Earth-based observation capabilities in November. The coming weeks will determine which theoretical models withstand scrutiny and which must be fundamentally rewritten. For now, the saga of 3I/Atlas unfolds as a live scientific experiment proceeding at interstellar velocity. With every new observation comes another chance to glimpse the physics governing worlds beyond our own. Even equipped with humanity's most sophisticated instruments, some cosmic visitors stubbornly leave more questions than answers. 3I/Atlas stands as a reminder of how much remains unknown about the universe beyond our solar neighborhood. What forged its unusual chemistry in the stellar nursery of its origin? How long did it wander through the frigid depths of interstellar space before chance brought it careening through our solar system? What other interstellar visitors have passed undetected, lacking the dramatic outburst that brought Atlas to our attention? The data streaming back from Mars orbiters, combined with the final Earth-based observations before the solar blackout, will provide pieces of this cosmic puzzle. But they cannot provide every answer. Some mysteries will persist long after 3I/Atlas vanishes from view, racing outward on a hyperbolic trajectory toward destinations unknown. What remains certain is this: humanity has witnessed something profoundly rare, an object from another star system, performing before our instruments for a brief window measured in weeks, offering glimpses into chemistry and physics that might be commonplace among the stars, but remain exotic within our familiar solar system. The clock is ticking. Every passing hour carries 3I/Atlas farther along its one-way journey, closer to perihelion, closer to the moment when it will either vindicate our understanding of cometary physics or force us to confront something we've never encountered before. The telescopes are watching. The orbiters are ready. The world's astronomers are coordinating across continents and time zones, united by a single urgent question: what secrets is 3I/Atlas carrying from the stars, and can we decode them before it vanishes forever into the cosmic dark? At mission control centers across 3 continents, screens flicker to life with the first post-perihelion data packets from Mars orbiters. The transmission delay, 8 minutes at current Earth-Mars distance, means they're watching events that already happened, ghosts of light from the comet's closest solar approach. Dr. Valente's voice breaks the silence in the JPL conference room. High-rise data coming through now. Resolution is, my God. The image materializes line by line. Where astronomers expected to see a single nucleus, possibly fragmenting, the high-resolution camera reveals something that sends a ripple of stunned silence through every observatory monitoring the feed. The nucleus hasn't fragmented into chaos. Instead, it's splitting with geometric precision, 2 distinct lobes connected by a narrow bridge of material, rotating slowly around their common center of mass. The structure resembles nothing so much as a cosmic dumbbell, each end measuring approximately 2.1 kilometers across, separated by a neck barely 400 meters wide. That's not random fracturing, Dr. Ortiz mutters, leaning closer to a screen in Madrid. That's tidal stress doing something we've never observed before. Within minutes, nomad spectroscopic data arrives, and the room erupts in controlled chaos. The CO2 to H2O ratio hasn't just remained elevated, it's stratified. The sunward lobe shows a ratio of 9.2, while the trailing lobe registers only 4.1. The 2 halves of the comet possess fundamentally different compositions, as if they were 2 separate objects that merged long ago in the depths of interstellar space. Dr. Sato's hand shakes slightly as she pulls up the spectral analysis. There's something else. The sunward lobe is showing emission lines we've never cataloged before. Complex organic molecules, amino acid precursors, in concentrations that shouldn't exist at these temperatures. The implications crash through the scientific community, like a shock wave. 3I/Atlas isn't simply a comet. It's potentially a binary system. 2 objects from possibly different stellar nurseries that collided and merged during their journey through interstellar space, each preserving the chemical signature of its origin. 3 hours after perihelion, Maven's plasma instruments detect something that shouldn't be possible. The comet is accelerating, not the predictable acceleration from solar gravity that's already accounted for in every model. This is something else entirely, a non-gravitational acceleration of 0.0043 meters per second squared, small but undeniable, pushing the comet slightly off its predicted trajectory. Outgassing, someone suggests immediately. Asymmetric jets creating thrust. But the numbers don't match. The observed acceleration is too strong, too sustained, and pointing in a direction that doesn't align with the primary outgassing jets visible in the imaging data. Dr. Valente runs the calculations 3 times, checking for errors that aren't there. If this acceleration continues, 3I/Atlas will leave the solar system 0.7 kilometers per second faster than predicted. That's enormous for a non-gravitational effect. The observation mirrors Oumuamua, the first interstellar visitor, which exhibited similar unexplained acceleration as it departed the solar system in 2017. But 3I/Atlas is actively outgassing, making it clearly a comet, while Oumuamua remained inert and mysterious. 2 competing theories emerge within hours. The first proposes that the sunward lobe, superheated during perihelion, is venting volatiles from deep beneath its surface, materials that were shielded for millions of years during interstellar transit. The thermal shock of perihelion has cracked open these ancient reservoirs, and they're now releasing gases with enough force to alter the comet's trajectory measurably. The second theory, more controversial, suggests that the rotation of the binary nucleus creates asymmetric outgassing patterns far more complex than typical comets. As the two lobes spin around each other every 8.7 hours, jets fire in a choreographed pattern that generates net thrust. It's rocket science, but natural, a cosmic demonstration of physics we've never witnessed at this scale. As 3I/Atlas begins its outbound journey, the Mars orbiters execute their carefully choreographed observation sequence. They have perhaps 72 hours before the comet accelerates beyond their effective range. Mars Express captures the full glory of the coma at its maximum extent. The HRSC camera reveals that the green luminescence isn't uniform. It pulses in concentric waves emanating from the nucleus, each wave representing a distinct outburst as fresh ice surfaces are exposed to sunlight by the comet's rotation. The false color images show the antitail has intensified, now stretching more than 100,000 kilometers sunward, a glowing spear of massive dust grains that defies every casual expectation of how comets should behave. TGO's Cassis catches something unexpected during a close approach observation window. The narrow bridge connecting the two lobes is glowing, not from reflected sunlight, but from its own internal heat. Material is flowing from the cooler trailing lobe toward the superheated sunward lobe, a slow-motion transfer of mass driven by thermal gradients and the centrifugal force of rotation. It's cannibalizing itself, Dr. Sato breathes, watching the process images. The sunward side is so volatile-rich because it's literally pulling material from the other half. This isn't two objects traveling together. It's two objects in the process of merging or potentially tearing apart. The data suggests the bridge won't survive. Thermal models indicate it's losing mass at approximately 2,000 kilograms per second, a rate that will sever the connection within 60 to 90 hours after perihelion. The question becomes, what happens when they separate? It happens at 2:33 Universal Time Coordinated on Halloween, October 31st, a cosmic trick or treat that nobody predicted. The bridge snaps. Mars Reconnaissance Orbiter's HiRISE, monitoring in time-lapse mode, captures the moment. The narrow connection between the two lobes tears apart, and suddenly 3I/Atlas isn't one comet anymore. It's two distinct objects, each with its own trajectory, each carrying its own story. The smaller, trailing lobe, dubbed Atlas B within minutes, begins tumbling chaotically, its rotation destabilized by the sudden loss of its companion's gravitational influence. It brightens briefly as fresh ice is exposed to sunlight, then begins to fade as its outgassing rate drops. Without the thermal engine of the sunward lobe to sustain activity, Atlas B will likely become dormant within days, a dark, frozen chunk of interstellar ice coasting silently out of the solar system. But Atlas A, the larger sunward lobe, explodes in a frenzied activity, freed from the gravitational constraints of its companion. It begins spinning faster, rotation period dropping from 8.7 hours to just under 6 hours. The increased spin rate flings material outward more violently. The coma doubles in size within 3 hours. The green glow intensifies to magnitude 10, briefly making it visible to large amateur telescopes despite the solar glare. And the non-gravitational acceleration increases to 0.0061 meters per second squared. It's a natural spaceship, Dr. Ortiz says, his voice filled with wonder rather than alarm. The outgassing is asymmetric enough, and rotation is fast enough that it's generating sustained thrust. It's flying. By November 3rd, as 3I/Atlas A and Atlas B separate beyond the effective range of Mars orbiters, Earth-based telescopes begin reclaiming their view. The solar elongation angle has increased enough for the most dedicated observers to catch glimpses of the remnants. What they see astounds them. Atlas A has developed a tail unlike any observed before. Not the classic dust tail, not the ion tail, but a hybrid structure that spirals outward like a Catherine wheel, shaped by the comet's rapid rotation and asymmetric jetting. It's beautiful and bizarre, a cosmic pinwheel announcing itself as it races toward the outer solar system. Atlas B, now a dark, silent companion, can only be detected by the starlight it blocks as it passes in front of background stars, a shadow in space, carrying secrets that will never be revealed. Dr. Valente releases the final trajectory calculations on November 5th. Atlas A will exit the solar system at 72.3 kilometers per second, notably faster than any gravitational model predicted. Atlas B will follow a slightly different path, separating from its companion by approximately 400,000 kilometers per year, as they both journey back into interstellar space. In 40,000 years, they'll enter the outer boundaries of another star system, perhaps to be detected by alien astronomers who will wonder at these strange visitors from distant suns. The scientific papers flood in throughout November and December. Nature publishes a special issue on 3i/Atlas, featuring 14 separate studies. Science follows with 11 more. The data reveals insights that will reshape cometary physics for decades. The binary interstellar comet hypothesis. 3i/Atlas proves that objects from different stellar nurseries can collide and merge in interstellar space, creating composite bodies carrying multiple chemical signatures. The thermal fragmentation mechanism. The separation event demonstrates that tidal stress combined with extreme thermal gradients can cause binary comets to fragment in predictable ways, offering new tools for understanding potentially hazardous comets approaching Earth. The green coma chemistry. The atomic oxygen emission mechanism is confirmed beyond doubt, but the extreme CO2 ratio suggests that interstellar comets may have fundamentally different compositions than their solar system cousins, shaped by the colder, darker conditions between stars. The natural rocket effect. The sustained non-gravitational acceleration of Atlas A demonstrates that asymmetric outgassing from rapidly rotating bodies can generate measurable thrust, potentially explaining similar anomalies observed in other comets and asteroids. Yet questions remain, questions that may never be answered. Where did Atlas A and Atlas B originate? What star was their parent? How long did they wander separately before their collision merged them into the binary system we observed? What other interstellar visitors have passed through undetected because they lacked the dramatic outburst that made Atlas visible? Dr. Sato, speaking at the December American Astronomical Society meeting, puts it eloquently. We caught lightning in a bottle. 3i/Atlas gave us a 3-month window to study a visitor from another star system under ideal conditions. We learned more about interstellar objects in those 3 months than in all previous history. But mostly, we learned how much we don't know. The universe is full of wanderers, she continues, her voice carrying to the packed auditorium. Objects cast out from their parent stars, drifting to the galaxy for millions of years, occasionally passing through solar systems like cosmic messengers. 3i/Atlas won't be the last. It might not even be the most interesting. Somewhere out there, right now, another interstellar visitor is approaching our solar system. We don't know when it will arrive or what it will teach us, but we'll be watching. We'll be ready, because the next one might not just be interesting. It might be the discovery that changes everything. On a cold January evening, a graduate student in Hawaii's Mauna Kea Observatory is reviewing routine survey data when she notices something odd. A faint point of light moving against the background stars, faster than any asteroid should move. She flags it for follow-up observation, not yet knowing she's just discovered humanity's 4th interstellar visitor. The universe, it seems, isn't finished surprising us. The dance of cosmic wanderers continues, and we're only beginning to learn the steps.